Well, in our next section, section 2.3, we're going to talk about the algebra of limits. Before we discuss that, though, we need to remember what the algebra of functions are that we're going to be concerned with. And that's this first definition. If you're given two functions, f and g, both of them with domain capital D and going into R, f plus g of x, a new function, is just equal to f of x plus g of x for every x in the domain. And number two, f minus g of x is equal to f of x minus g of x. Number three, f times g of x is equal to f of x times g of x. And the fourth one, f over g of x is equal to f of x over g of x. Now, one thing definitely needs to be stated about this. In this definition, these three functions, the first three, have domain D, capital D. We might be restricted, though, on this one. This, number 4, the division function, maybe I'll write all of these have domain capital D, but this one is going to be the domain D minus all of the numbers or points where g of x is equal to 0. So I will say remove the set of all x such that g of x is equal to 0. So if g of x is never equal to 0, then the domain is simply capital D. Now we'll move on to Theorem 2.4. And it is analogous to Theorems 1.8, 1.9, and 1.11, but for sequences. So I encourage you to go back and take a look at those sequences. Notice there are 4 parts to this theorem, but there are only 3 sequences. Well, just like in this definition, I believe the book left out the f minus g, and they just assumed that it's understood that if f plus g of x is equal to f of x plus g of x, then f minus g of x would be f of x minus g of x. So this one was left out in both cases. That's why there's not four corresponding theorems here. Because after all, to get from here to here, you could simply multiply the function g of x times -1, and you would end up exactly with this. So Theorem 2.4 says, same setup. We've got the same two functions, f and g, domain capital D and going into R. And we need to let x be an accumulation point of the set D, the domain D. And let's remind ourselves, as I frequently do, about what an accumulation point means. Well, accumulation point of D does not necessarily need to be in the set D, but every neighborhood around it. So if that's x naught, and this is x naught plus, say, delta for some little positive number, and x naught minus delta. Although x naught might not be in the set D, there must be an infinite number of elements from this interval that are contained in D. That's an accumulation point of D. Okay, well, if f of x has a limit at x naught, namely the real number capital L, so the limit as f of x as x goes from x naught to as x approaches x naught is the real number L, and the limit of f of g of x as x goes to x naught is the real number m, then we have these 4 following equations. The limit as x goes to x naught of f plus g of x is exactly what we would expect. The limit of f of x plus the limit of g of x, L plus m. And likewise in the minus case, this limit would be L minus m. The third one, when you multiply the two functions together, the limit would be, as we expected, L times m. And the last one, also as we would expect, the limit as x goes to x naught of f over g of x is L over m, but this one we need to put one of these provided by statements in there. And I think I'll do it the way the textbook says, even though it's a little bit too restrictive. I will say, provided the limit is not 0, we couldn't even write L over m if m were 0, and g of x is never 0. I'll say g of x is not equal to 0 for all x in the domain. So that says that in the domain, g of x is never equal to 0. That is a little bit too restrictive, and I may talk about that in a future chapter. All I really needed to say was that g of x is not equal to 0 in some little tiny neighborhood of x naught. But we'll talk more about that later.